Hello and welcome. Welcome to the next session of RoboLaunch. We're delighted to have you with us here as we continue to explore robotics with researchers from around the world. Today, we're going to be joined by Dr. Tapomayukh Bhattacharjee, and he's going to be discussing his research at Cornell University. I'd like to turn the session over to the RI Summer Scholars that will be hosting today's session.
Hello, my name is Stefan Hedges-Kessel, and it is my pleasure to introduce Dr. Bhattacharjee, an assistant professor specializing in robotics at Cornell University. Dr. Bhattacharjee runs the Emprise Lab at Cornell, which seeks to enable robots to assist people with mobility limitations in completing daily activities. His work spans the fields of human-robot interaction, haptic perception, and robotic manipulation, with the goal of leveraging robot world physical interactions in unstructured human environments to efficiently and safely perform daily activities. I have approximately 30 of my fellow scholars in the room with me and a number more online. We're all very excited to hear your talk on building caregiving robots. Thank you.
Thank you so much. Thank you for having me today. It's my pleasure to virtually meet everybody. So my name is Tapomayukh Bhattacharjee, but it may be difficult to pronounce, so you can just call me Tapo. And as I've been already introduced, I am at Cornell. I am an assistant professor here, and I run the Emprise Lab. And today, I'm going to talk to you about building caregiving robots. Now, the way I have structured this talk, it's in a very high level, but hopefully it will give you some ideas about how to go about this if you're interested in this field. But feel free to interrupt me if you have any questions at any point of time. Right. So in general, my research goal, or my lab's research goal, is to enable robots to assist people with mobility limitations with activities of daily living. Now, what do I mean by activities of daily living? So, for example, if you look at these different images, right? You can see humans or caregivers assisting people with feeding, with transferring them from wheelchair to bed, or even dressing or other activities, such as meal preparation, cleaning, and things like that. According to a survey in 2014, around 24 million adults in the US needed assistance with tasks of daily living. I believe around the world, the number is around 140 million. Now, these activities of daily living, as you can see, they're very different from one another, right? Like there are these basic activities such as feeding, dressing, transferring that you will do every day. And there are some of these instrumental activities, right? And these are activities that help towards those basic activities, such as housework, laundry, meal preparation, and etc. Right? Now, there is such a wide variety of activities of daily living. How do you even go about, having robots to help with this? Now, the complexity is not just due because of the variety. Caregiving by itself is a very multifaceted and contextual problem, even for a single activity. So let's look at an example. For example, here on the left, you will see a person, Tyler. He is being fed by his caregiver while he's watching TV. Look at it very closely, how this is happening. The person brings the food close to their mouth, and then Tyler leans forward a little bit to take the bite, right? Now, even for the same activity, this feeding activity on the right, you will see another caregiver, William, is actually assisting Henry with the same activity. But look at how they do it. Like here, William is going to pick up and see how carefully he goes and puts the food on one side of Henry's mouth. And that is because these two care recipients, even it's the same activity, they have different causes of their mobility limitations. And so on the right, Henry has a basilar artery dissection. On the left, Tyler has a C1, C2 spinal cord injury. And because of that, on the left, while Tyler can move his neck a little bit, on the right, Henry opened his mouth, and then William had to put the food inside the mouth around left molar, because that's where he can actually chew the food. So even with the same activity, you can see, depending on the care recipients, and their different functional abilities, the assistance mode can change. Now, it's not just that, right? they can also have different behavioral traits. Well, let's look at the video again. Here you see Tyler is watching, his favorite activity is actually watching baseball. So Tyler doesn't even care when the care recipient is bringing the food, caregiver is bringing the food. He just keeps on watching the TV, and care recipient just kind of interrupts him and brings the food near his mouth, and Tyler grabs the food. But look at the video on the right. Henry, to show that he wants to eat, he actually shows an intent by looking at the person, looking at the particular the plate of the food item, and that's how William knows that, okay, this is time to feed. So they have different behaviors. So we talked about users' behaviors, we talked about users' mobility limitations. But there are even more factors, right? Look at this task. We're looking at the task of feeding. Look at the task of transferring. Now on the left, you will see Henry is being transferred. See how William just picked him up and put him on the wheelchair. But here, the same William and Henry, they are trying to move him. They're doing this activity in a very different way. He's bumping onto his legs so that they don't cause spasms, and he's able to lift up using this lift. And so here, you can see that even the caregiving assistance not only depends on the care, like the care recipient, but also their environment. If the environment has this device, they could use that device, or the caregiving mode can change depending on how it works. And finally, depending on who is assisting them, the way you assist them can also change. So for example, again, on the left, you see William is trying to put on a pant on Henry. And so when he lifts up the pant and then puts the pant directly, right? On the right, Jane is also another caregiver, cannot actually lift up the leg so easily. And so she does this assistance in a very different way. Takes on the light, bends it, and then she puts on the pant. So again, basically the point of showing you all these videos is that not only caregiving is like very challenging because there are so many different activities, but even for a single activity, it is a very multifaceted and contextual challenge because it changes based on the user's behavior, like what they want, what their preferences are. It changes based on what is their underlying condition of disability. It changes based on who is giving the assistance, their functional abilities, and it changes based on the environment. So hopefully I've convinced you this is a very, very, very challenging field, right? Now the question is, should robots help with these activities? And can they help with these activities? Now let's go back to this feeding example, right? Now the caregivers are actually doing a wonderful, like really wonderful job of helping care recipients with these tasks. But even after that, I mean, when I chatted with them, I went to these facilities and I talked to them, there is a huge lack of control and independence, right? Like imagine yourself asking somebody else to feed you every morsel of bite in your day-to-day life. You just feel like you are not in control of the activities that you do. And sometimes care recipients told us when we went there that sometimes they even feel embarrassed to ask everybody every time for help, right? Sometimes it can be socially challenging as well. And it's not just from the care recipient's point of view, even from the caregiver's point of view, turns out these activities can be very time consuming. Some activities more than others. Feeding, for example, is an example where caregivers say that it's a very time consuming activity and it can increase caregiver burden. And so you can see that robots actually should help with these kind of things if they can actually do these tasks successfully. And it is a multifaceted problem. But then the question is, can they? Well, okay, good that robots should help, but can they help? These are very complex tasks. Turns out that they actually have the potential to help. Like, for example, this is a company, Kinova robotics company from Canada. You can see these robots, this is a robot arm. It's mounted on a wheelchair, on a person's wheelchair. And these people are able to use these robot arms to do activities such as opening doors, opening drawers, picking up different things, objects, or even interaction with different humans and things like that, right? So for example, here, see that? And so for like these robots, they enable them to do these tasks and interact with people around them that they love without having to depend on somebody else, right? Here is another story to show that robots actually have the potential to help. Okay, no worries. But basically, Henry Evans, you already saw him before in the previous thing. And you can see that Henry, basically this was a Robots for Humanity project. It was started by Willow Garage, the company that no longer exists. And Henry, what you are seeing here is Henry is being assisted in different tasks from Jane, his primary caregiver, who also happens to be his wife. And the idea was that Henry actually saw a robotic demonstration in CNN. And then he reached out to my previous lab, my PhD lab, where I was doing my PhD, and said, can these robots help me? And that's how this project started, where Willow Garage collaborated with Georgia Tech and some other labs to be able to do various tasks for Henry. For example, here, you will see a couple of examples. Henry, apparently, using this robot for the first time in 10 years, was able to scratch or itch or even shave himself, right? And that gave him a lot of independence to do these tasks. Even though these tasks are like, these are only the first steps, but you can see how robots can enable these people with disabilities to do tasks that they otherwise won't be able to do by themselves. Okay. Now, all these things are great, and these robots have the potential to help. But as I showed you before, it's a very challenging task. And so, some of the main challenges here is that, in addition to the complexity of tasks themselves, how do you even go about building these robots, right? Like, think about this. Let's say you are in a lab, and you need access to care recipients, like people with disabilities, to be able to test out your algorithms or your systems, robotic systems with them. And that's not easy, right? There is a huge lack of access to care recipients. There is also lack of access to realistic environments. The environments that I showed you in video, that video, those are in real homes, in assistive homes. They are also a little bit different from normal homes that many people live in. They have some modifications done for these people to be able to live there in an accessible way. How do you even get access to these realistic environments? And of course, in any area of robotics, there is this challenge of expensive robotic hardware. So then the first question that comes to mind, okay, before building robots, actual robots, which should be deployed in the real world, can simulations help? Well, in robotics, I'm sure you have already seen, I'm coming towards the end of the summer. I'm sure you have already seen many different talks where, you will see that, people use simulations to be able to come up with different control policies for robots, right? Whether it's manipulation, whether it's robots walking, robots manipulating things, or things like that. Problem is, how do you develop a simulation environment where you actually have realistic human beings with disabilities there, and these environments that are with assistive environments, not just normal home environments, but assistive home environments, right? And that's why I want to first introduce you this recent work out of my lab, which we called RCare World. It's a robotic caregiving world, primarily led by two students, Rajat, who is a first-year PhD student, and Ruolin, who is an incoming PhD student. So what does RCare World do? RCare World, let me start by showing you a video. Here you see an environment where you use the Toyota HSR robot to pick up a strawberry and feed a person. And you see the person is moving, like the hands are, there's a tremor. This is actually, it's not, it's actually because this person has cerebral palsy, right? And so using RCare World, we collaborated with medical school, Columbia University's medical school. We collected real data from people and their mobility limitations, like what is their range of motion, how much they can move their arms, like how do you develop these human avatars? And we developed 6 different care recipients with different disabilities. On the left, you see a person with C1, C3 spinal cord injury. In the middle, you see C4, C5 spinal cord injury. Then C6, C7. Then you see cerebral palsy. That's the human avatar you saw in the previous strawberry feeding video. And also you see left side hemiplegia and brainstem stroke. So these avatars were built by collecting real data, clinical data, and then we spend time in building these human avatars. Now that's one aspect, right? I mentioned about care recipients. So these are realistic care recipients. We also developed realistic care homes, as I mentioned. So these care homes, as you can see, they have assistive devices such as hospital beds that can actuate, Hoyer sling devices, stair lifts, wheelchair lifts, bathing chairs. Also different levels of accessibility of home environments. Normal home environments with some accessibility modes with different, levers for doors, wheelchair lifts, different bed heights and things like that, that actually represents an assistive home environment, and as well as different other skills that we. So we developed these, and these are again developed by collecting from data from universal design manual of how to build these assistive homes. In addition to that, because assistance needs physical and social interaction, we need to be able to come up with realistic interactions. And that's where we developed these human models, which not only have realistic motions, but also realistic physics, by actually developing musculoskeletal models. So these human models, we have 2 kinds of different human models. One is a musculoskeletal human model, and one is also skeletal human model with soft tissues over them. And we model each of the muscle in the human body in the simulation. And so that enables us to get forces that you see through interactions, which can be a little bit more realistic than articulated human bodies that are there in some of the simulations that are, right? Now, once we did that, we developed some experiments, for example, for different tasks, such as a robot putting on a pant on somebody when the person was sitting on a wheelchair, a robot moving their arms, robot feeding, robot going and helping them in different things. And so the simulation environments enables you to learn policies, different reinforcement learning policies in simulation, using these realistic human models and realistic benchmarking tasks. And then using this, we actually transferred these tasks from the simulation, let's say in this case, a bed bathing scenario, to the real world where as purpose. And the forces that you see generated on the right side, you can see they are not perfectly matching, but they are close. But that's just physical caregiving, sim to real transfer. We also talked about social caregiving, where here you'll see a robot is actually helping a person to do some exercise. And the person can wear a VR interface, and based on that, they can not only see the robot, follow the exercise, and robot can also monitor their progress and then tell them how to change their caregiving activities. Like, for example, how to change their exercise mode, or if they were able to not do a particular step in the exercise, let them do it again. So again, you see that by using this robotic caregiving simulation world that we developed, it at least enables us to prototype these systems before we jump to the real world, using realistic care avatars like care recipients, realistic care homes, and other general robotic capabilities, right? But simulations are great. That's great for you to get started. But that is definitely not the end of the story, because ultimately we want people to be helped by these robots in their real homes, and real people helped by real homes, right? So then the question comes that, let's say once you prototype this, how do you build a caregiving robot? You actually build a caregiving robot. To be able to do that, I am going to focus on a particular activity. There are many activities of daily living, as I had mentioned. And I'm going to particularly focus on one particular activity, which is robot-assisted feeding activity, where the idea would be for a robot to feed people who cannot feed themselves. So to talk about how we went about building this caregiving robot. Now, even though I'm showing this in the feeding task, many of these things, the framework of how to develop a caregiving robot applies for other tasks as well. So to develop this, to start this, we basically, first I want to introduce this work. It's called Sparks. It's also another recent work from our lab, led by my two first-year PhD students, Rishabh and Rajat. And there, the idea is, again, to go back and look at these activities from the human side first. Because we as engineers, even though we can develop these systems without actually understanding the human side first, there may be a gap between what we develop in the lab and what people actually need in the real world. And so, first, basically, it comes back to the same thing, that caregiving is multifaceted. And now let's look at this activity, the same activity. I'm coming back to that same activity of Tyler being fed by his caregiver. In this case, it happens to be his mother. So it's contextual on, as you saw, the user, which happens to be the Tyler. As you saw, depending on the user's behaviors, user's disability type, the assistance changes, right? So the caregiving changes. So it depends on the user. It depends on the environment, everything around them, like where the TV is, what they're looking at, what the surrounding environment is, where the bowl is, where the table is with the bowl and the bottle of water and things like that. Because when you want to develop a robot that does that activity, it matters where is the robot, what is the environment around it, where are the obstacles, where are the objects and things like that, right? And it also depends on their caregiver, who is giving them as assistance. Now, this is on the human caregiving side. For the robot caregiving side, in addition to this, it depends on the robot. Which robot you use? Because if you use one particular robot, let's say Kinova Gen 2 versus Kinova Gen 3 versus Fanka or something like that, your robot kinematics is different, everything is different, and that means your caregiving also changes, right? The assistance that you will give, the robot will give to these people, that will change. So using Sparks, what we were able to do is we'll say, okay, let's first understand the human caregiving problem, how they solve this problem, like how human caregivers feed human care recipients, and then try to transfer it to the robot side. That's how we'll build this caregiving robot, right? So in Sparks, the first two steps are about understanding the human caregiving, where we basically look at these building blocks, this user's environment, user environment, their caregiver, all of these, we call them as building blocks. We find out what these building blocks are, and we build what we call task workflows for human caregiving. What does that mean? But what we mean by task workflow is how are human caregivers doing this activity? How are they picking up the food? How are they bringing the food to a person's mouth, right? And the building blocks talks about the users. So we analyze the user, how much they can move, what their mobility limitations are, what they can do, right? For example, think about this. If a person could actually move their neck, the robot doesn't have to put the food inside their mouth. They can bring it close to the mouth, and then the person can take the last step and take a bite. But for another user who cannot move their neck, the robot needs to go inside their mouth and feed them. And that's why it's important to first understand the context of it. Once we understand the human context, our goal is to implement the robot side. And that involves 3 steps. Those are, again, now we will add the robot to this building block, so that we'll again instantiate the building blocks for the robot caregiving. And now we will transfer the task workflow that we made for human caregiving to the robot caregiving, because depending on the robot, how we do the task is different. And then we'll actually perform those actions. And that's what we call the action workflow. And in this video, you actually see the result, the final result, where once we understood how human caregivers fed human care recipients, You can see here, people with spinal cord injuries from C1 to C6 spinal cord injuries are actually being fed by our robot in the lab, different food items. So we are able to learn from what humans do and then move to the robot side, right? So now let's go into a little bit more detail. How did we learn? Like we said, okay, we first understand the humans and then we do these 3 steps and this is the final result. But what are the basic insights inside? Like how did we actually move from there? And so for that, there are 3 things that we thought are useful to understand, right? It's basically 3 contexts, we call them. First is the technical function, which is, what is our task here? We want to have a robot that can feed people. So can it actually feed people? Can it actually pick up a food item from a plate or a bowl and feed people? So we want to make sure that it can actually, the technical function is possible. Next, that's important, is technology robustness. What that means is, does it only work for one food item? Does it only work for one particular environment? And so the question here, here we looked at, how about the robot suddenly comes up with an item that it has never seen before, like the human, like the caregiver, the care recipient wants to eat an item that the robot has not seen before. Can it feed unseen food items? And then finally, once we develop the technology, that's great. But the most important thing in any of these assistive technologies is, what's the point of developing the technology if users won't use it? So we need to see, do users actually feel empowered by using this technology? I mean, that was the whole point of this research, right? We showed that care recipients feel embarrassed asking somebody else to feed them every morsel of bite. We told them that caregivers feel burdensome when they have to feed people. And so the question is, then are we actually solving that problem? Do users actually feel empowered? And will they actually use this technology in their homes? Let's say in future. So we need to answer all these questions to be able to move from those human caregiving to the robot caregiving. And I'm going to go over this sequentially. First is the technical function. Can it acquire bites and feed people? So when we started this research, I was wondering, like, how difficult can it be? Like, we as humans, we eat food all the time, breakfast, lunch, dinner, we eat food all the time. Like, how difficult it can be to pick up a food, right, from using a robot. So just went ahead. This was when I was doing my postdoc at University of Washington. I went ahead, took a fetch robot, put a fork on the fetch robot, and just developed a very simple control policy. Basically, it says the robot goes on top of a plate and then just goes down as a fixed policy. It goes down at a fixed depth. We know where the table height is. So it goes down based on that, and we pick up food items. And turns out this simple policy actually works, as you can see here, right? The robot was able to pick up this this watermelon, right? But it actually failed for many other food items. And so the idea then that what we realized was that, I mean, it actually is a very challenging problem, right? Think about food items. Food items have so many different physical characteristics. Like, some items are hard, like carrots and celery. Some are soft. Some are slippery, like banana. And they have different compliance, different texture. And that's just picking up the food item. And then also, how do you feed them? And that's another, like, it's a very interesting handover problem. Like, how do you take the food so that it's easy for the person to take a bite and they don't feel it's cumbersome, right? So it's actually more challenging than we originally thought. So then we thought, okay, how do we then even start by making a robot that can feed people, like do the technical function? We said, again, coming back to the original point, we humans are experts at doing this. So let's study ourselves. Let's study humans. So we basically did an experiment in the lab where we basically asked people to pick up food and feed this mannequin as if they're feeding another person. And they probably ate or they fed people with the most expensive fork that they would ever eat with. There's a fork instrumented with force sensors that can measure forces. And on the end that you see, like flower-like thing, that's a motion capture. So we wanted to see how they move, right? And this study opened our eyes. Like, it's about the complexity of this task. Like, for example, look at what's happening here. This person wanted to pick up a piece of banana and it fell off, slippery, right? I mean, it happens to all of us. But then this person did something and it was successful. The person was successful in picking up the banana. What happened was, when we looked at the data, was the person changed the angle of the fork when they pick up the food. It may not be conscious, they're used to it. But what happened that when you change the angle, the gravity vector created a component which acted along the frictional direction. And so that helped the banana stay on the fork. So you see, physics plays a lot of role in these activities, right? We found out that people use this like different visual and haptic properties to pick up these different food items. So once we had this idea, we wanted to develop an algorithm that robots can use to pick up these food items. I'm not going to go into the details of this algorithm. I'm happy to answer questions if anybody has this, but the general idea is this. I'm going to explain you on a high level what the idea is. The high level idea is the robot sees an image of a plate. Then using some network, deep learning network, it puts them into different bounding boxes. And then for each of these food items, it figures out using another network, which we call SPANET, like skewing position action network. It figures out what is the right action to pick up a food item. Basically, it can pick up based on the different actions that you can take. It can figure out what would be the predicted success rate, and then it will select the action that is likely to be the most successful. What action should it take? Based on that human experiment, we had created a taxonomy. We found out what are the different actions that people take, that humans take, and then we programmed those actions on the robot. And then with this algorithm, the robot was just trying to decide, given these actions, which action should I choose given this food item? And that's what this algorithm does. So here you see the result. The robot autonomously goes, picks up an utensil. It happens to be a fork here because we're looking at solid food items. It goes on top of a plate. Using the camera, it looks at different food items. You see, it can classify different food items, identify it, and then algorithms tell it how much force to apply and what actions to use to pick up different food items. It goes in front of the face. It detects the face. It comes near the mouth. Here we assume that the person can move the neck, and it gives it to the person so that it's easy for the person to take a bite. In this case, because it was a carrot, instead of going just horizontally, it tilted itself so that the person could take a bite easily without having to open their mouth wide, right? And what it was doing is it was picking up the food that we call bite acquisition. It was timing it, when to feed, and then it was transferring the food item so that the person can take a bite. So we developed this. And so we thought, okay, we have the technical function there. Like the robot was able to pick up food items and feed people. But then let's come back to our original list, right? This is not the end of the story. We need to think about technology robustness now. Can it feed unseen food items, like food items that it has not seen before? This neural network was trained on a set of 20 food items or so. How can it pick up unseen food items? And it's a genuine challenge, because if you go to a typical grocery store, there are like around 40,000 items, right? Like, food is diverse. And so the question was, how do you pick up food items that you have never seen before? And this particular work was led by a PhD student, Ethan, at University of Washington when I was a postdoc there. And the idea was to use online learning. What that means is, instead of just having a state, and then based on the state, you taking an action, which we did before, we want to have a feedback loop. We want to see, once we take, because we don't know what is the right action to take, we'll explore some action, and we'll observe the reward. Like, the reward in this case can be is the item on the fork or not? Like, was the robot able to successfully pick up the item or not? And then you can update your policy, and you keep doing this, right? And you keep doing this, and that's how you converge the right action. So again, it's the same thing, but the only difference is in the bottom, there is a feedback loop now using the dashed line that you see. The top part you already saw, like given a plate of food items and the bounding box says it should be able to tell what the food item, what action to choose. But because if it's an unseen food item, we don't know what action to choose. It will just select an action based on some algorithm. And that will trade off between exploration and exploitation. And then it will observe the reward. Is the food item, in this case, is the banana on the fork or not? And then just this binary reward, and based on that, it will update the policy. Again, I'm not going to go into the details of what exact algorithms we used, but I want to give you an idea of how the system works. So once we did that, here you actually see the robot actually, when this experiment started, did not know how to pick up the banana. And the right action is this red bar. And you see originally the confidence was low, but as it kept on trying, the confidence became higher and higher, and it converged to the right action. But once it learned the right action, it did not forget how to pick up different food items. And next time it saw a banana slice, it was able to pick up the banana slice. Remember what action it took, and it was able to pick that up. So here again, you saw we are only by no means we have solved every way of technology robustness, but at least we have started taking the first steps towards looking at, okay, how can your technology adapt to situations that it has not seen before? In this case, particularly picking up unseen food items. So now let's come back to the original list. We talked about the technical function. The robot was able to pick up certain food items and feed people. We talked about technology robustness. The robot was able to at least generalize to some unseen food items. Now comes the big question, right? Will users accept this technology? Otherwise, what is the point in developing this in the lab if people don't want to use it? And that's where we went back and we did the experiments with actual people, like users with spinal cord injuries. And when we did this experiment, we did a study. We wanted to find out, because every user is different, this is the primary thing we learned, every user is different, which means the system that you develop needs to be personalized to the particular user that you are giving assistance to. And so based on that, the robot, we decided, we tested different things. We tested different speeds, interfaces, dining scenarios, and modes of autonomy. And I want to particularly focus your attention on the mode of autonomy, because that's a very interesting result we found. Basically, what we did was we experimented 3 different conditions. We said, one is full autonomy. We want to say, oh, the robot should be completely autonomous. Robot selects the food, picks up the food item, and feeds the person autonomously. The second was partial autonomy, which means the user, out of those byte acquisition, byte transfer, and byte timing phases, only one phase was automated. Everything else the user controlled. And the other was low autonomy. Everything the user controlled. Okay. Now, what's the catch? Why? Well, because we told them that, as you know, in the real world, there is a lot of uncertainty. And even though we may want to always make our robots autonomous, there is bound to be failures in the real world. Something may happen, go wrong in the user's dining room or kitchen, and the robot may fail, right? And so to actually give them that experience, we also artificially introduced errors. Errors in the byte acquisition, where you can see the robot here failed to pick up this particular strawberry. This was deliberate. The users don't know this is deliberate. We introduced them randomly. We also introduced error in the timing. The user is ready. See, he's opening the mouth to be fed. Robot is not coming. The user is like, what's going on, right? And so it's delayed. That's also, we artificially introduced this delay. And then We also added an error on the transfer side, where instead of coming near the mouth, the user, like the robot, perceived the mouth to be somewhere else and fed something else in the air. And then we asked them, what do you prefer? A fully autonomous system which can give these errors, or a partially autonomous system where you have some control over the robot's actions, but there will be very little errors? And the answer that we found was very interesting. We found that people with higher mobility limitations, like C1, C2 spinal cord injury. So for folks in the audience, just to let you know, C1, C2 spinal cord injury is much more severe than C6, C7 spinal cord injury, okay? So people with these high mobility limitations, they said they preferred more autonomy even with errors. Like Tyler, for example, one of them mentioned, like, even if the robot fails 1 in every 3 trials, I'm happy to use this robot because this makes a huge difference in my life. But people who had C6, C7 spinal cord injury, who had some movement in their arm, they said, I have very high expectations of the robot. If autonomy results in some errors, I would rather go with partial autonomy. I am happy to give the robot some commands. It is not going to give me a lot of workload, like stress or workload, but I would still prefer accuracy because I have some movement anyway. So you see, caregiving is very contextual. Depending on the user's behaviors and their functionalities, their disability type, the mode of assistance that you need is very different. That's the central message that I want to bring through this talk, which is when you want to build caregiving robots, you have to go back to the actual users, actual environments, actual caregivers, and understand the problem and understand that there is no one fixed answer. It's a very contextual problem. But regardless of that, people felt that when we talked about the technology acceptance, people are very excited about this technology. For example, you can see here, the technology allows me to do more things on my own, of course, giving me more independence and making me feel more free, and gives me something to look forward to. That's an amazing comment, right? And so that tells us that even though we are just barely scratching the surface in this impactful field, there is a lot of scope and there is a lot of hope for real impact. So this is how we actually first studied human caregiving and then gradually moved to implementing these robotic caregiving solutions. To kind of bring it back on the high level, right? Assistive feeding in general is a very high impact but technically challenging task. And it brings together many subfields of robotics, whether it's representation and state estimation, whether it's manipulating deformable objects, whether it's legible motion planning, social dining, eating with friends and family instead of just direct scenarios, like interface design, shared autonomy. How do we change the level of autonomy? Inferring the intent of the human, all of these areas, right? So it's a very multifaceted field. Here are some open data sets and hardware for people, like if you're interested, use this. But before I conclude the talk, I want to bring it back because I understand most of the audience are either high school students or just beginning undergraduate students. I want to bring it back to the broader question of, assistive robotics, that's great, but how do you actually become a roboticist, right? And the things that I have seen through my experience that have become useful is that whatever level you are, let's say you are in high school right now, and you are studying chemistry, mathematics, physics, all of these things, everything has some role to play. Mathematics, like probability statistics, is like the basic, like all kinds of Bayesian methods, like some of these methods, I didn't go into the details of these algorithms. It's fundamental. Linear algebra, it's fundamental to this. So all of this is important. Physics, as you saw, the way we got the insights for these manipulating deformable objects, physics is very important. Statics, dynamics. Chemistry, well, not so much for this particular task, but material sciences, and that affects robotics as well. All of these things that you study in a high school or even in a beginner undergraduate courses, it's important. In terms of the skills, analytical skills are very important, but also coding skills. Like whether it's Python or C++, That's important. ROS, probably most of the people in this audience know, but if you don't know, it's a robot operating system. Learning ROS is very useful. But ultimately, everything you learn will add value. And once you go like beyond these fundamental courses to become to advance and to do robotics research, interdisciplinary courses are very important. Whether it's you take courses from on mechanics and design, from mechanical engineering, or control systems for electronics and ECE, or artificial intelligence and perception courses from CS, or even human-robot interaction, which is interdisciplinary by itself. All of these can play a role, right? And once you do this, once you graduate as a roboticist, you can either go to industry, you can be a robotic software engineer, hardware engineer, or even researchers like AI researcher, computer vision, motion planning, HRI, controls. Or you can be like me and choose a faculty career, right? But the take-home message is robotics is interdisciplinary. And especially for the area of assistive robotics, it's almost impossible to come up with a technology that will make a real impact if you do not consult the stakeholders. And by stakeholders, I mean care recipients, the patients, the caregivers, the occupational therapists, and things like that. So their inputs are essential. And these robots cannot be stiff. They need to be flexible because every user is different. They need to be able to adapt to users' preferences. And whenever all of you in the audience, you are like among the select few who can actually make an impact through these state-of-the-art technologies. But whenever you develop this technology, you have the capability to develop this technology. I would encourage you to always think about the impact of the technology that you are developing on the society. That's how I generally tend to think about the research that I do. What the stuff that you are doing today, how is it going to impact the technology in future? So to conclude, in general, my work is on enabling robots to assist people with mobility limitations with activities of daily living. And this is me. Thank you.
Thank you so much for your talk. I thought your results on autonomous preferences were particularly interesting. We'd now like to open up the room for some questions. I think we'll begin with scholars here in person. If anyone has a question, they would like to come up. All right, if not, then we can go to, oh, yeah. Yeah.
Hi, thank you for your talk. It was really interesting.
Thank you.
My first question was that you mentioned that the level of autonomy for the manipulator is different considering the recipient, right?
Yes.
So what all independence did you give to the recipients in the low autonomy case? Like, did you have like a shared teleoperation or something like that, or was it just limited to selecting what food item or like?
Very good question. Very, very good question. So one thing that we need to think about is our users here are not healthy adults, right? They are people with disabilities. And so teleoperation is completely like out of the picture here, because I will tell you an example. I didn't give this example today. We actually interviewed some expert users of Kinova robots, like people with disabilities who have been using Kinova robots for years. And we asked them, like, can you try picking up different food items just by completely teleoperating the robot? And just to pick up 1 or 2 strawberries, it took them 45 minutes. So the idea was that so it's a very good question that you said, where you asked, even though we say low autonomy, it's not fully teleoperated. What I mean by low autonomy is the robot, like, they will choose some high level decisions. For example, hey, do a scooping action, or pick up the banana using a tilted action, or things like that. And once they select, let's say, tilted or scooping or something like that, the robot has these primitives programmed so that it can adjust the primitives based on the food item's location and its current location to actually do the particular activity. Same thing for transfer and things like that. So yeah, what they were doing was selecting these discrete high-level actions, and the low-level control policies were still executed by the robot.
Okay, thank you so much. I have another question. Like,
yes,
this is very trivial, I guess, but you mentioned that like like, for example, you gave the action of picking a banana using a fork, and
Yes.
like you like demonstrated some failed attempts in grasping.
Yes.
So like when we actually like have a failed attempt, like there is a hole created in the banana, right? And if you try to grasp the banana at the same position, it will
Yes.
fail again. So
very good point. Very good point. So I will tell you, this is an assumption that we did for the contextual banded study, the online learning study, where basically we assumed that the context do not change much. What that means is we replaced the banana slice after every try. Having said that, you're absolutely right. That's why this is still an open area of research, which is we found that we were able to pick up the banana slice with like around when the robot had no idea what that is, with like around 10 attempts. If we try 10 attempts on a given banana, it will be destroyed, right?
Yeah.
And so we need to still think about how to come up with actions that can converge faster. And if we want to do, how do you do this? So that's an interesting research question. Another question is, which comes back to the autonomy question, right? Maybe once it fails 1 or 2 times, if it realizes that this is a very fragile food item, maybe it can defer to the user to be able to help them directly, assuming the users are expert themselves. So that's also another question, whether you want to try to do this completely autonomously or you want to defer to the human depending on the situation. But again, very good question and very keen observation.
thank you.
Yeah, thank you.
Hello.
Hi.
Hi, I have a question about safety.
Okay.
So, I mean, with these robots, you're having these possibly powerful robot arms interacting very closely with people, and you're explicitly moving like sharp objects towards someone's face.
Yes.
I'm just wondering how you approach safety and how you might deal with situations where people might want to overpower a robot to get it out of an unpredictable situation.
Yeah. Very good question. Very good. I'm glad you asked this question. So it's probably one of the most important problems to think about, right? But when I think about safety, I want to talk about 2 things here. One is like actual safety, like the robot doesn't really harm the person. It can do the task without harming the person. And another is perception of safety. So let me first talk about the actual safety. For that particular actual safety thing, the way we did this was, the fundamental thing is users should have complete control and they should be able to stop the robot at any point of time. Now, with a typical healthy adult, you can stop the robot by pressing emergency stop or things like that. But people with disabilities, these people do not have even sometimes have the power to press an emergency stop. So what we had to do, and which I did not cover here, we had to build a system where we had to connect the robot's controls using a particular device called Tekla device to the interface that they were using. So some of these users were using sip and puff. You sip and puff and you control things based on that. Some of the people were using head trackers. So we connected the robot to those devices themselves, so that if at the last point, if something happens, the user should be able to stop the robot completely using the interface that they're used to. But that's like the highest level, right? Even before that, the way we did safety was we did 2 different steps. First, for this particular demo that you saw, it was with people with spinal cord injuries, and people who could move their neck a little bit. So it went and it stopped before, and we had a collision model around the person's face and body, which can move based on where the person is. And the idea was the robot never violates that collision model. So it will never go inside the food item, inside the person's mouth, but it stops right before it. And then the person goes in front and takes a bite. Now, what if it violates that? Then we had those force-stop sensor, right? And that we trained so that if it goes above a comfortable force threshold, the robot stops immediately. So we had these 2 levels of safety. And then on top of that, we had this particular thing where the person can stop the robot at any point of time. Now, that's the actual safety part. But there is also the perception of safety. And that's where we did that study. If you remember, I didn't cover the details here, but we looked at, okay, even if the robot may be safe, but these people don't know what's going on inside the hood. So if the robot comes towards my face at a faster speed, I may be scared. I may not want to use the robot. And that is related to the perception of safety. And so there, based on the user, we change those things, like such as what speed it approaches, what trajectory it takes, and things like that, so that they feel safe. That's how we did this. But having said that, again, this is only initial steps. There are many things we still need to do to make it truly safe and deploy it in the real world. But that's the way we are approaching these things.
Okay, thank you very much.
Thank you.
All right. If not, then yeah, thank you so much for your talk. This is really interesting.
Thank you. Thank you.